So hi, today we will discuss about the flyback converter. So this is one of the most commonly used isolated power converters. So it's a DC-DC converter, but it is an isolated converter, and we will derive the equations. So here you see a evaluation board, a sample design. Again, I think you will be able to understand which components is what. Again, you can see the capacitors at the input and output. I don't know, probably there's a diode here, and that is probably the controller. I don't know, that Q2 is the switch probably, and it has like 3 legs, either MOSFET or similar device. And again, we have switches, capacitors, but there's not like conventional inductors like a toroid inductor or air core inductor. Instead, we have that kind of component, which is probably a transformer. Okay, so let's see how the flyback converter evolved. So actually, you can start directly from a buck boost converter. So here you have the input, a switch, a diode, capacitor, and inductor. So as you remember, what you do is, it is like a boost converter. You close the switch, you charge the inductor, then that inductor current, let me draw it, so whenever it is on, you are charging it in that direction, and whenever it is off, it is flowing in that direction. So you are storing energy on that inductor, then you are transferring it to the capacitor, right? So what I can do, I can technically just divide the same capacitor into 2 parallel paths, and they can be in the same core or not. So what is if they have the same turns ratio, and again, don't get confused with the dots yet, but you can think like the same current, it's a one-to-one mutual inductor or one-to-one transformer. So the same current flows from here and here. Okay, so then what happens? Okay, what happens if I just cut the connections in between, right? So the idea is, so again, this is, let's say, like an ideal transformer for now, and whenever you close that switch, so you will have some current, and the same current will pass through here, right? But then, again, we know the transformers only work with AC, actually not like pure AC, but it should be stated like that. If you give a constant DC current, then the flux in the transformer increases and saturates the core. Okay, so then, that is how the flyback converter evolved, and we will derive it. Then the real advantages, instead of using a 1-to-1 transformer, maybe you can use a 10-to-1 transformer ratio as well, right? So that means the voltage on the primary side will be, let's say, the voltage at the secondary side will be 1/10 of the primary voltage. So suddenly, you have, or it can be vice versa, it can be 1-to-10 ratio, but as we discussed in the previous video, suddenly then you have the option to play with the transformer turns ratio to adjust the output voltage, and you can get a higher conversion ratios. Okay, so then we are actually modifying that one. We are moving our switch to the downside, so actually it can be switched on and off easily. And secondly, okay, in the previous one, the direction of diode is in that direction, because that was the case with the buck boost converter. But instead of getting negative voltage, it's isolated, so it doesn't really matter. What I do is, I just use some reverse polarity inductor. So that means you are winding it in one direction and the secondary is in the other direction, but at the end of the day, it is the same things. The only thing is the secondary current direction reverses. Okay, so that you reverse the diode, or you can think like you just moved everything upside down, and you have exactly the same circuit. Anyway, so we have that thing. But before, again, like if you have an ideal transformer here, it will not work. Okay, we should have a proper transformer model in order to understand how flyback converter works. In order to do that, let's go back to our third year course, and you have, let's say you have an ideal transformer, and in an ideal transformer, of course, like you have that thing, and let me write it here. So V1 over V2 is equal to N1 over N2, or you can write it from the current, I1 times N1 is equal to I2 times N2. So actually, if you increase the number of turns here, so you will have a step down transformer, or you can choose a higher number of turns on the secondary. So let's say if it is 1 to 10, then that means that transformer increases the voltage by 10 times, but decreasing the current by 10 times, because we cannot increase the power. Power should be conserved, right? So anyway, the convention is something like that. So again, that core, normally in an ideal one, we assume infinitely permeable core, and normally we have some like leakage current. Okay, so in an ideal, if it is ideal, then you assume no leakage flux. But in reality we know neither the core is infinitely permeable, nor there's not all the core, all the flux is trapped inside the core. And also, those conductors are not perfect. They have some resistivity, and a better model, as we have seen last year, is to use some realistic transformer equivalent circuit, and it is something like that. So R1 is the resistance of the primary windings, L1 represents the leakage flux, that kind of things. Again, similarly, R2 is the resistance of the secondary coil, L2 is the leakage flux on the secondary winding. We have Rm or Rc, so that represents the hysteresis losses in a transformer, so it's just dissipating heat. And we have Lm. So Lm is the magnetizing inductance. So in short, what happens if you just disconnect the secondary? So at the end of the day, even if you remove the secondary winding, it is a coil wrapped around the core. So just the primary winding becomes like a inductor. So Lm is mainly due to the inductance. So you have, this is the leakage flux, and this is the mutual flux, the coupling flux, and Lm is the remember, the inductance by definition was the flux linkage created by current, or N times phi divided by current. Okay, so Lm is due to that inductor. So this is the full model of a transformer. But again, we will simplify it, but we will not use the ideal model. Let's ignore, for that conversion, and we will discuss why we can ignore other components. But for now, let's ignore the resistive parts. Okay, so let's ignore that part, and that part, the core resistance, and also the leakage components. Okay, so what we end up with, the mutual inductance and the ideal transformer part. And as we will see, that mutual inductance is really important for the flyback converter. Actually, that is how you store energy and send it back to the secondary site. Okay, so again, for polarity, so it has like the same polarity here, but if you use an opposite polarity, the only difference is like you have the current direction. Whenever it is entering in that direction, it will flow inside of the core, and the voltage will be reversed. So it just changes the direction of the voltage and current. So our flyback converter is basically like that. Again, the polarity of those things, I mean, if you look closely, the one direction is opposite for the primary and secondary winding, and we have a switch here. We have one diode, a capacitor, and our load. Again, we will assume that capacitor is large enough and our output voltage is constant. So we will see how that circuit behaves, and let's try to calculate those characteristics. So I can represent that system like that, okay, and because of that polarity, I1, when I1 is getting in that direction, actually I2 is coming from here and going out, and when V1 is like positive polarity like that, V2 is reverse, but we still have like let me write it here. So V1 over V2 is equal M1 over N2. Oops, sorry, N2, right? Or I1 times N1 is equal to I2 times N2. And this was coming from the fact that MMF balance, remember, when you make the closed loop, then you will have that relation. Anyway, so let's try to, again, first I will not get into the mathematical calculations. Let's try to understand the main concept, and once we understand the main operation modes, then we can derive the relation between the input and output voltage. Okay, so let's try to plot the operating modes. So first, what happens when the switch is closed? So our switch is here, one is closed. So you have Vs voltage coming through in that direction, okay, and once you have Vs, actually current, again, if current is flowing in that direction, it would like to flow in the opposite direction, okay, it would like to flow in that direction, but we have that diode. That diode is important for our operation, and now that diode is reverse biased and it becomes off, okay, so diode is off. So once diode is off, then I know that I2 will be equal to 0, and if I2 is equal to 0, that way I1 getting into the primary winding is also 0. Suddenly, this is not a transformer because we are not sending any power to the output, but still it is an inductor. Why? Because it is still a core, so it is as if there is no current here, so that one is removed, but it is still a coil wrapped around a core, and actually LM models that one, and it is like a boost converter or buck boost converter. In that manner, we close that one and we are charging that inductor. We are charging that inductor during the on period. So where does that current flow? It will flow through LM. Okay, so let me write that one. LM charges during on period. So again, I will show all those slides later on, but let me plot it. So for that time, okay, let's say this is ILM, okay, so during that period your inductor is charging linearly. Why? Because VLM is equal to Vs. So actually you can calculate the slope of that thing and it will charge up for D time Ts. Okay, and diode current or the I2 is 0, and actually in that period our capacitor is supplying our load. So capacitor is being discharged, but our again we assume the capacitance is large enough, so the output voltage doesn't really change much, but in reality we know it is now an RC circuit and it decays. Okay, so that's not the interesting part. So during switch on we have nothing, but we have just the inductor, and it is charged the same way if it is like a boost converter. So what happens if I turn off that switch? Okay, that is the interesting part. So if I turn off that switch, now I have some current in that ILM. Okay, so that current would like to flow that way, but now that way is off, so it cannot go that way. Instead it will go like that, right? It will go that way, and from that source you are not taking any current because it is off. So in the on cycle you charge your inductor, so now that inductor would like to flow in that direction. So if it is flowing in that direction, okay, ILM, and that will induce a secondary voltage in that way, and that will you have the diode here, so diode becomes on, and suddenly you are charging. Okay, so now you are charging, capacitor C is being charged, and that LM is being discharged. Right, again the voltage level here will be proportional to N1 and N2, and we will derive that in a minute. So but at least, you know, please try to understand what's happening. So at first we charge the inductance LM, so it is not working as a transformer, but the energy stored, again if you think about it, let me draw that one. So if you think about from the magnetic circuit point of view, okay, so you can write the flux core. So what is the flux inside the core? Okay, so actually that was, again we will discuss why it is not starting from 0, but it is again charging up. And similarly, okay, similarly if you can plot the B flux density, again that flux density, again we will derive the mathematical terms, but it will be B core. Okay, so they are increasing, so you are storing, again remember, you know, the energy stored, and again it's time axis, but normally if it is BH axis, so you are storing energy in the core during the on cycle. Then you are discharging that energy. Okay, you are discharging that energy. Let me try to draw it here as well. So if you think about that one, so if this is ILM, first you charged it during DTS, and then you are discharging it, right? So at the same draw here, this is DTS, and this can be flux core. So similarly, flux in the core is increasing, and in the second cycle it is decreasing. And somehow if you just keep the switch long enough, that B, I mean, again if this is a completely linear system, or if you assume it is linear, yes, it will keep increasing, but in a practical system for some time the flux will start saturating. Okay, so we don't want to keep them long enough. We would like to put the flux or flux density phi or B within some limits. Anyway, so in the second part you have your inductor current, first you stored the energy in the inductor, and in the off period that stored energy now being transferred to that capacitor, but using some voltage ratio. Okay, and with that voltage ratio actually you can obtain either quite high or quite low conversion ratios. Okay, so let's again discuss the voltage waveforms. And actually we have I mean, in the presentations, I'm not going to open it, but you can click on that link. So there's an online animation for the flyback converter, right? Anyway, so during on time it is being charged for 1 minus d time ts, it is discharged, and it goes like that. And for source it is exactly like a boost converter, so you only get some current from the source during the on period. So it is, you know, that it is that portion of the waveform, then you don't get any current from the source. And for diode, for diode it is opposite. Whenever you are drawing current from the source, the diode is off, so it's not going like that, and it is the other part. But you know, it is not exactly the same current. Okay, so it is not the same peak and minimum like we have here, because there's a conversion ratio. Okay, don't forget the N1 and N2 terms. Anyway, we will drive those things. And actually, if you look at the capacitor, again, capacitor current, again, I assume C is quite large. Which way it's positive, I don't know. Let's say the positive is in the that direction. So whenever the diode is off, so whenever that is that way, so our, sorry, let's define the capacitor current like that. Okay, so whenever it is off, your capacitor is being discharged with some constant current, and then the same diode current minus the load current is being charged your capacitor. And actually that one is also important, and that is our VLM. Okay, whenever, okay, we will drive that one. So whenever it is on, VLM is Vs. Okay, VLM is Vs, and VLM is equal to V1 as well, right? And whenever that one is off, so now that voltage can be calculated. If that voltage is VO, okay, that is VO, so in the second half you have VO here, and the input voltage is minus VO because of the polarity, times N1 over N2. If N1 is larger than N2, then you will have larger voltage here, or if N2 is larger, it's vice versa, right? So in the second half, so that voltage is directly seen by the inductor here, LM here. So that's why we have minus VO times N1 over N2. So that part is quite critical. Okay, so as you can imagine, actually we can just calculate the voltage relation between input and output by just using these two areas, but actually it is not the only way, so I will try to do the other methods as well. So first let's start with the similar method, voltage seconds area of the inductor, or we can use the flux. I mean, at the end of the day, again, you will have the flux in the transformer, so you can use that equation. Or even, I mean, you can, for the capacitor, you can the same thing, like you have voltage second balance for an inductor, or current seconds balance for the capacitor. So you can use all these three to calculate the voltage relations. Okay, so let's do that. So let's start with the voltage seconds balance. Okay, so let me get rid of myself. And actually I know during on period, okay, so this is, remember, this is the TS and this is 1 minus d time TS, and during on period I have that area in the inductor, so it is Vs times d TS, okay, and that area is equal to what? It is equal to that area, or I mean, if you would like to use the negative, then you can say that area plus the actual value equals to 0. I mean, let's do that. And in the second time, again, remember the voltage, okay, let me clean that part a little bit. So in the second part, okay, the diode is on, so once if you have output voltage here, that output voltage is seen on the primary side as minus VO because of the polarity times N1 over N2. Okay, so that is why I have that voltage, and let me write that one, VO times, okay, N1 over N2 times 1 minus d TS is equal to 0, right? So that is my equation. Again, you can get rid of the that variable immediately, or you can write Vs d is equal to VO times N1 over N2 1 minus d, or you can write VO divided by Vs, okay, that is equal to d divided by 1 minus d times N2 over N1. So before proceeding on the different derivations, let's discuss that one. So again, remember that one is derived from the buck boost converter. So we have the buck boost converter gain ratio here, d minus d divided by 1 minus d multiplied by the transformer ratio. Okay, so that is the most important thing. So now you don't control the output voltage only with duty cycle, but you can control it with turns ratio. Of course, the turns ratio is not being changed during operation, but let's say you would like to increase your output like 10 volts. Okay, so if you would like to increase your output voltage by 10 volts, instead of using very, I don't know what will be, let's say around 0.9 duty cycle, okay, instead of using a 0.9 duty cycle where you will have more ripples, and also the inductor current, or also the current ratings of the MOSFET has to increase. What you can do is you can use a turns ratio N2 over N1 as 10, or let's say N1 can be 1 turns, probably not, but N2 is like 10 turns, and then you can operate your transistor around 0.5 duty cycle, okay, where it is most optimum for ripples and switch ratings and that kind of things. Or even, for example, maybe you want to reduce the output voltage by 100 times, okay, and then actually you can adjust those things and you can still run your duty cycle within some realistic parts. Okay, so that is the flyback converter, and let's do the same calculations just for the sake of completeness from other parameters as well. Okay, let's calculate it from the flux circuit. Again, I mean, our flux, okay, our flux actually increases the flux in the core during on period, and it's being reduced linearly during the discharging period. And let's write in that area of the flux. Okay, so again, let's say we have some flux, and that is equal to what at t during, let me write here, during on period. Okay, we have the initial flux, okay, and plus something. So if this is our initial flux, how can I write that line? Actually, that is really the relation between the inductance and the current, because again I would like to write here again, it is lambda over I, the current, the inductance, or it is n phi divided by I, right? So you can write that one, and actually for on period, okay, let's go that one. So on period, okay, Vs is equal to what? I mean, normally if this, let me go back that one. So you can write, I mean here, okay, that voltage here, let's say V1 is equal to what? M1 times d phi over dt, right? So I can write that relation. I'm again, you know, the inductor current calculations, they are probably the easier, but calculating flux is important, because in 2 weeks time we will be doing magnetic circuits, so I would like you to get familiar with those concepts. Anyway, so I can write, okay, V1 is equal to N1 times d phi over dt. So during on period, what I can do is Vs is, because it's connected to source voltage, N1 times d phi over dt. Or I can write the change, okay, the change of flux is equal to Vs times delta t divided by M1. Okay, so I can write that equation like Vs divided by N1 times t, or if it is again linear, or I can write flux at dTs is equal flux at 0 plus Vs divided by M1 times dTs. Okay, I can write that one, and actually that value will be the peak. Okay, that will be the peak flux. I mean, that is important, because actually if you divide that number with the cross section of the area, then you can calculate the flux density. And once you start designing magnetic circuits, again you will realize if flux is large, then you know you can't get a material with having like 10 Tesla, 100 Tesla. It has to be limited, let's say, within 1 Tesla. So if you would like to get a high flux, that means you need to use a high cross-section area for the core. Okay, so let's continue with the off state. So this is the peak flux, and let me write it here. So that number is important for us. Peak core, that is to prevent saturation. So how can I write that part? Okay, so that part, in that part, basically our circuit becomes like, now that one is disconnected because it is off, but now this part is being conducting. So now it is proportional with the output voltage and N2. Okay, the discharge characteristics of that one is dictated by the output voltage and the secondary number of turns. So let me try to write that one again. What you can write in that period is, now you can define it from the peak value, okay, peak value of the core minus, okay, V output divided by N2 times that time, and that time is equal to 1 minus D time Ts. I mean, output voltage is that voltage, in the second one, and the flux is equal to N2. Why I am using N2? Again, I would like to write it here. So it was in the, let me write it on period, and for off period what I have is V2 is equal N2 times d phi over dt. Okay, and V2 in the off period is equal to V out. Okay, so and that will comes back to here, and if I calculate it, that will be equal to initial value. Again, under steady state, I say that value has to same with that value. Let me put all those parameters here, 1 minus d ts, and that is d ts, right? So okay, I can combine that one. That was the peak flux, so I can put it here. So it is, let me write here, plus Vs divided by M1 time dTs minus Vo divided by N2 1 minus dTs is equal initial flux. So it is actually no different than writing the voltage second balance for the inductor. It is the same relations really. So anyway, so let me put it completely. Vs divided by M1 time d is equal, let's get rid of the ts as well. It is equal to Vo divided by N2 times 1 minus d, right? Or V out divided by Vs is equal to d divided by 1 minus d times N2 divided by N1. It is exactly the same relation, right? So it is exactly the same relation. Again, you can do the same thing by using the capacitor current. Then you need to calculate the peak values and that kind of things. I leave it as an exercise for you. Okay, but that is the characteristics of the flyback converter, and we have flexibility due to that turns ratio. And actually, I would like to you need to calculate again the peak. For example, let me go to original circuit. You need to calculate the peak values of the inductor current and voltage, peak values of the diode current, and that kind of parameters for selection. Again, if you are choosing a practical application, you need to consider that kind of change, and that peak values will be defining factor for the MOSFET's current rating. Again, that peak value will be the defining value for the size of the core, blah blah blah. Okay, again, you need to calculate what is the stress levels, voltage stress levels on that switch. So again, please have a look at your textbooks, and those equations are given there, and in the following weeks I will solve a couple of examples. Anyway, so let's move on. And again, I'm skipping that switch selection for now, but there's calculations for that in your textbook, how the peak value of current is calculated in terms of output voltage and current. And again, for peak switch voltage, I mean, that should be like in our graphs, it is Vs now. So if you think about it, whenever the switch is off, so there is some Vs voltage here, and plus there is some minus, because of that one is open, minus Vo multiplied by M1 over N2. So if this is like 0 points, that voltage is added up, so you see a larger voltage stress. I mean, this is like one of the disadvantages for the switch. So you see a higher voltage stress on the switch. Okay, it's higher than the source voltage actually. Okay, and actually again, if you can put instead of output voltage, you can write our calculations, and you will see it is N2 and M1 cancels each other, and you will have 1 minus D times Vd. Please, again, please drive that one as an exercise. Cool. So again, in next video, I will solve an example in discontinuous conduction mode. And in the discontinuous conduction mode, it is similar to the DC converters we have seen in the first semester. So your switching period can be short, or maybe the output current is low, whatever. So the idea is then your off period is longer, so that the capacitor, the inductor charges up, then it is not fired again until it discharges. Okay, it just comes down to 0, and then you will have 0 current for some time. And again, like in the first semester, it seems like a disadvantage to run a converter in discontinuous conduction mode, but actually it is commonly used for flyback converters, especially for small size flyback converters, because it helps us to limit the flux density, so you can actually use a smaller core, right? And furthermore, your switch or diode is actually reaching to 0 voltage, so in the next turn on you are not doing a hard switching, right? You are not turning on or off the switch while it is carrying a current. Instead, its current for the switch is already 0, so you are just turning it on smoothly. So it helps you to reduce your switching losses, both on the diode and on the switch, if it is designed properly. And again, you will see it in your term projects when you are trying to implement your system. There are some converters which use variable switching frequency, right? So that T doesn't have to be constant, or you don't have to just keep the switching frequency constant and change the duty cycle. What can be done, depending on the operating conditions, is play with the switching frequency as well, so you can get quite a high efficiency under different operating conditions. Anyway, so we will see some examples of that one. Okay, and please have a look at that reading materials, like how does it works, and the comparison between DCM and CCM. And there are also some variations of the flyback converters. Again, we are not going to analyze them numerically, but maybe you can use it also in your term projects, or probably you will see them in your professional lives. So the first one is the 2 transistor flyback. So in that 2 transistor flyback, the idea is, instead of just using T2 here, the rest is same, we add another transistor there, okay, and 2 more diodes. Okay, 2 more diodes. So you can say, what's the purpose of that? Why do I have to use like 2 extra diodes and 1 transistor? It comes from the fact that in our assumption, okay, let me go back quite a lot. So remember, in our actual model, we have some leakage flux here, L1, okay, and we have Lm. So we ignored Lm, and in reality, yes, L1 can be small enough, but there always exists some leakage flux. And what's happening is, in a normal, let me put it here, so if you have a leakage flux in that system, okay, so you are closing the switch, so that leakage flux, that Lm current is nicely flowing through here, but the current in that ILL, okay, have nowhere to go. Okay, so again, if you just model the system using an ideal switch, you will have infinite current here, infinite voltage here, because that VL for that one is equal to LL times DIL over DT, right? So that will create loss of voltage, and that will increase the stress on that switch. Even if your switch is not ideal, okay, if the current levels are high and if you are switching it at a fast rate, then you can create some voltage stress, some ringings, and that extra voltage will damage your MOSFET. So in your hardware projects, we would like to see how you included that leakage flux. Okay, so let's look at in that one for the 2 transistor flyback. So even if you have a leakage flux here, okay, normal with that, just that T2 used, so that current has nowhere to go. But with that configuration, so now, I mean, again, you can control those ones. They don't have to be like opened at the same time. But let me draw somewhere here, right? There's where the leakage flux is. So whenever you opened it, that extra flux now will have path to go to the source. So instead of just dissipating that energy, so if you have a capacitor at the input voltage level, so you can store it there. Again, we are not doing mathematical analysis in this course for that converter, but you may use it in your hardware projects and you can see it in some applications. Please have a look at those reading materials for that 2 transistor flyback. Another option is to parallel many flybacks together, so you can have that kind of configurations, because again, one disadvantage of the flyback, remember in the Chuk converter you have the inductor at the source and you have nice and more or less steady current from the input, where the flyback converter, it is like the boost converter, you have some current then off, some current then off. So actually that can be prevented, and again the cost can be reduced. For example, let's say you have a flyback converter of 100 watts, and instead of designing another one for 200 watts, you can connect 2 of them parallel, which is reducing your cost. And furthermore, you can put a phase difference between these openings, okay? So whenever that one is on, that can be off. So whenever that one is off, the other one can be on. So you will have more or less, constant current. So you can overlap those things, and it will be a nice waveform for your input. And similarly, again, if you look at for the size of the capacitor, if you just use one flyback converter, whenever the switch is on, so that diode is off, and the capacitor has to supply all the load for off period, for on period. However, again, if you adjust those converters with a phase difference, so whenever one of them is supplying current, the other one can be off, and whenever that one is off, the other one can supply current. So you can reduce again the voltage ripples at your output. Okay, so again, using parallel converters is commonly used in different topologies, and also it is quite advantageous for the flyback converter. So that's all I would like to say. Please derive those equations yourself, and I will also upload an example solution on the flyback converter. Thank you.